Thank you folks all for coming. I really appreciate it, and how nice to see a full house again after all the years everybody staying home and watching on Zoom and so on. So welcome back. Welcome back to real life. I'm Ted Blank. I'm a resident here in Fountain Hills, and while I wish I was a NASA employee, I'm actually a volunteer whose job it is to talk about the missions that your and my tax dollars are funding and returning all this incredible science. So I'm happy to talk about this, and some of you may have come to some of my other talks about the Juno mission to Jupiter, the Mars rovers that are driving around on Mars right now, the Ingenuity helicopter that's flying around on Mars, where there's only 1% as much air as we have here on Earth. So think about how dangerous helicopters are on Earth, and then try to imagine one on Mars where you take away 99% of the air. They did it though. It's flown 30 times and it's still doing well up on the surface of Mars. So the engineers work very hard to make that happen. But today we're going to talk about the James Webb Space Telescope, which was launched just a little over a year ago to an invisible point out in space about 1 million miles away from Earth. And this telescope is a real tour de force of technology, and you may have read that it took a few extra years and a few extra dollars to get it ready to go out into space. But there were good reasons for that we'll try to cover today. Feel free to ask questions along the way. I'll try to finish up in just an hour, but I'll certainly stay around afterwards if you have any questions. How many of you have heard of the Hubble Space Telescope? Yes, everybody, right. Well, just to give you an idea of the relative sizes of the two, the Hubble Space Telescope has a mirror about 6 feet in diameter, and the James Webb Space Telescope mirror is about 18 feet in diameter. It had to be actually folded up in order to fit into the rocket that launched it into space. So that was a challenge as well, because telescopes tend to like to be made out of one solid piece of glass, and so when you unfold a telescope like this, you try to line up the segments within an accuracy of a 50th of a human hair. It's a challenge, especially since there's no way to go out and fix it like there was for the Hubble. The Hubble was serviced 3 times because of some problems with its optics, and then to replace solar panels and to replace reaction wheels, and some of the instruments were upgraded as well. We could do that because it was only about 320 miles or above the Earth. That's where it orbits right now. But the James Webb Space Telescope is about 1 million miles away, and since we don't have a space shuttle operating anymore, this is the challenge. Get it right the first time and don't make a mistake, because there's no way to fix it. And we'd hate to throw all that money down the drain. The telescope itself is sensitive to a different kind of light than you and I are used to seeing. The Hubble Space Telescope is sensitive to visible light, just like you and I can see, and visible light is a very narrow portion of the whole electromagnetic spectrum. Now, we have sent telescopes into space that are sensitive to much shorter wavelengths, like X-rays and gamma rays. It's very hard to focus a telescope that's trying to reflect gamma rays, so they don't use mirrors or lenses, but those are very high energy particles, but they can tell us things about space that no other different particular area of the electromagnetic spectrum can actually tell us. But if you move out into longer wavelength, like microwave and radio waves, we've got radio telescopes on Earth, of course, like the Very Large Array in New Mexico, and the Wilson microwave anisotropy mapper, which actually orbited at the Lagrange point as well, that same point that the James Webb Telescope is at, 1 million miles away. And that's sensitive to microwaves. You might have heard of something called the microwave background radiation. That's a very low frequency wavelength radiation that's left over from the Big Bang, and it was the detection of the microwave background radiation left over from the Big Bang was one of the confirming experiments that gave us the confidence that the Big Bang actually happened. So that was interesting. But the Hubble, the James Webb telescope is actually sensitive to infrared light. Infrared light is light whose wavelength is just longer than the red light that we can see. So we sense infrared light primarily as heat, those red heaters that give off infrared rays that you can stand in front of and get warm. That's infrared radiation, and that's near infrared radiation. The infrared spectrum is kind of divided up into near infrared, mid-infrared, and far infrared at just arbitrary points. And the James Webb telescope has instruments that are sensitive to both the near infrared and yes, please. Yeah, we'll turn off the light so we can see better, thank you. And the far and the mid-infrared radiation wavelengths, but not so much in the far infrared. So this will give you an idea if you've all, there we go. That's better. Thank you. You might have remembered from high school physics that wavelength and frequency are inversely related. So the longer the wavelength, the lower the frequency. And these waves are very long. So radio waves can be meters long. Any ham radio operators here? Right, so you know that you can sense, you have to have antennas that are really big because some of the waves that come in have a wavelength meters long. But the wavelengths that the Hubble and the James Webb are sensitive to are much shorter than that. Visible wavelengths and near and mid-infrared wavelengths. So we have to do something interesting. The detectors for the James Webb have to be cooled, very cold, in order to be able to be sensitive to the infrared waves that are arriving from distant stars and galaxies. And one way to do that is to send it far out into space, where it's very cold, but in order to chill the instruments down, they actually had to come up with a way to shield the instruments in the telescope from the heat of the sun, even though the sun is 94 million miles away. The heat of the sun shining on the telescope instruments would still heat them up to the point where they would be overwhelmed by that amount of energy, and they couldn't actually detect what they're aiming at out in space. So we've got lots to talk about for that. This is how the Hubble mirror was ground. You can see this roughly the size of the mirror, about 6 feet in diameter. It was created at the Perkin-Elmer-Danbury Optical Laboratory in Danbury, Connecticut, where I used to live. I didn't know this was going on in my backyard at the time. I wish I had. I might have gone down to check it out. But you may have heard that when this was launched into space, there were some problems. The Hubble telescope mirror could not focus light the way it was designed to do. It had been perfectly ground to the wrong prescription. Perfectly ground, but to the wrong prescription. So instead of a star being focused to a single point of light, this is what the first image of a star looked like when it was transmitted down to the ground from the Hubble telescope 30 years ago. Huge disaster. It took a year and a half to figure out what had actually gone wrong. And you can see that when you tried to take a picture of a galaxy, it kind of looked like you were looking through cotton wool or through an aquarium. Big disappointment, huge disaster, and lots of investigations as to what actually went wrong. So here's what actually went wrong. And part of the reason that the James Webb Space Telescope took an extra 10 years to get ready was because they did not want to have something like this happen again. There was some test equipment in the ceiling of the laboratory where they were grinding the mirror, and every once in a while they would wash off the mirror and put it underneath the test equipment and shine laser light down through it, and the laser light would bounce around in such a way that the mirror test equipment was designed to show perfectly concentric rings on the mirror when it was ground to the perfect prescription, and they hit that prescription absolutely right. In the old days, they would use something called a refractive corrector to do that. It had a lens in it. Perkin-Elmer said, we have a better idea. We have a reflective corrector that we can use to measure the curvature of the mirror. And so we'll put this in the ceiling. It cost $1 million to build this thing. We'll shine laser light through it. We'll put the mirror underneath it. And if we see perfectly round rings on the mirror through the interference of the wavelengths of light, we will know that the mirror is exactly ground to the right prescription. The problem was this. In installing this device in the ceiling, they had to shine a laser onto the end of this little rod, which was exactly the right length. You can see right there. And so the technician who put it in shined the laser light down and got a reflection. But instead of getting a reflection through a little pinhole on this shiny metal rod, he got a reflection from a little piece of the cover where some of the black paint that was supposed to be non-reflective have flaked off. And so this ended up being installed 1.3 millimeters lower than it should have. And 1.3 millimeters at the ceiling turned out to flatten the edges of the mirror by about 1/50,000th of an inch. And that was enough to, and in optical terms, that's like driving to Chicago and ending up in New York. A 50,000th of an inch is something that optical technicians would have to retire over if they made that kind of an error. So a lot of them did, I suppose. So that was the problem. So what did we have to do? We had to send some prescription glasses up to fix Hubble's disfigured optics. And so the shuttle was launched in space, and one of the instruments was removed, and something called CoStar was installed in its place, and CoStar had several little reflective mirrors and lenses that were ground to a prescription that would exactly return the light to the focal point that it was supposed to have if the main mirror had been ground perfectly. And it worked perfectly. So we were able to get photographs. The only problem with this is that the device blocks out 1/4 of the field of view that the camera inside the telescope has. So if you look at some Hubble telescopes, they look like the letter L many times. And that's the reason. The upper right corner was sacrificed because of the problem with the telescope. That's where the prescriptive optics are that return it to good prescription. And so we still get good photographs, but we have to take a little extra time to get that other quadrant filled in. Now, the James Webb Space Telescope, as you can see here, was basically funded first in 1996, and it was launched on Christmas in 2021. The time frame that you see here is all involved in testing, in measuring the mirrors, making sure that it would unfold properly in space, making sure that the heat shields would reflect properly, that no heat would leak from the instruments up, the radio instruments that talk to Earth. None of that heat would actually leak up into the space telescope itself and cause the instruments that are cameras to actually warm up. They actually found that some of the wires that went from the cameras down to the instruments that would radio the pictures back to Earth, they were only 4 or 5 feet away from each other. They found that these wires were made of copper, and they were thick enough that heat was actually traveling up these wires and causing the picture in the camera to actually degrade by raising the temperature of the camera. So they had to actually reduce the diameter of the copper wires so they wouldn't carry as much heat up into the cameras and cause them to warm up. They have to be almost 400 degrees below zero in order to work properly. So here's what the main structure of the telescope looks like. You can see those 18 holes. That's where the segments of the mirrors will be placed once they're delivered and installed and created and tested and polished and everything. And the telescope itself has to be folded up like this in order to fit inside what they call the fairing of the top of the largest rocket that we can make, launched in French Guiana by Arianespace. On top of an Ariane 5 rocket. This origami-like unfolding process has to happen on the way out to this spot 1 million miles away, and there's no way to bring the telescope back if anything goes wrong. There were 178 individual release points if any one of them had hung up or failed to operate the way it was supposed to, the entire telescope would be unusable. So that was really, really something. So here are the 18 mirror segments in protective cases. The entire mirror, when it was assembled, was placed into this giant bake and shake chamber, pumped down to near vacuum, refrigerated down to zero, down to almost 0 degrees Kelvin, almost absolute zero, as it would be out in space, and then shaken to bits to make it sure that if anything was going to break, it was going to break here on Earth and not on the way out into space after that rough rocket ride through the atmosphere. So here's a couple of more pictures of it, sort of folded up here, unfolded in the middle, and then here we see it with the mirror segments actually attached. They're covered here with protective covers, but the light would come from distant galaxies, hit these mirrors, be focused up onto this secondary mirror up here, bounced back down through this little black hole, and the cameras would be hiding behind the mirror system just through that little hole. And that's where those cooled cameras would be sensitive to the infrared light. The idea is that the telescope mirrors have to focus that light on a perfectly flat plane so that the camera is exposed. Every part of that chip is exposed evenly, and you get a perfectly focused and perfect picture. Where does the power come from for this beautiful device? It comes from solar panels. And you can see here that the solar panels have to be pretty large because this spaceship is 94 million miles from the sun. So these solar panels unfold out in space. Again, everything has to be folded up to fit inside the nose cone of the rocket. They unfold out in space, and here you can see a test where they're supported, of course, by segments on straps from the ceiling. This is designed to operate in zero gravity, so it wouldn't be able to hold its own weight up in Earth gravity. So this is a test to make sure that all that works well. And all this power is then funneled back into the telescope to operate the equipment, the cameras and the chillers, and of course the radios that send these pictures right back here to us on Earth. So here's a little video about the mirrors themselves.
Also had to go through a crazy journey. The 18 giant hexagonal segments that form Webb's mirror are made from a metal called beryllium. This metal was chosen to keep the overall mass of the mirror extremely low, while still retaining lots of strength. Despite being about 3 times larger than Hubble's mirror, Webb's mirror only had a fraction of the mass. But in order to construct these perfectly polished mirror segments, they had to make 14 stops at 11 locations all across the U.S. The first journey started in the mountains of Utah, where the beryllium powder was mined and shipped to Ohio, where it was purified and turned into individual mirror blanks. Then the blanks were sent to Alabama, where each one was machined into a honeycomb structure to reduce mass. The next destination was California, where the mirrors were polished to the exact shape, perhaps the most crucial part of the process. After this, the segments made several trips across the country, undergoing years of testing to check that they were polished correctly. On the next journey, the mirror segments traveled to New Jersey, where gold was evaporated over them inside a vacuum chamber to form a very thin coating. After some more testing, the mirror segments ended up in Maryland, where they were assembled together and attached to the main instrument module.
So you can see that this process takes a long, long time. And one of the reasons it took so long, of course, is because the mirrors themselves had to be ground perfectly and tested. No one wanted a repeat of what happened with Hubble, and it would have been absolutely unforgivable if that had happened. So every possible check was made to make sure the mirrors were ground perfectly and assembled right. The amount of gold on those mirrors is something like 10 to 20 atoms thick. That's all that's required. And the reason they use gold is because gold is a really good reflector of the infrared light that this telescope is sensitive to. So, but the amount of gold, like 1 gold Krugerrand would have been enough gold to coat all 18 segments after it was melted and vaporized and deposited on the glass, on the beryllium surface. So here's what the telescope looked like during a test when it was folded up for storage inside the rocket nose cone before launch. And there it is, ready to be packed up and sent to French Guiana for launch. So this was the container that the telescope was placed into. Inside this container there was approximately 1 particle of dust in every cubic meter of air. It was that clean to make sure that absolutely nothing would contaminate the telescope or its mirror or its sunshield or its instruments or any part of it. It was trucked to a ship, it was launched, loaded aboard the ship, went through the Panama Canal, and eventually made it to French Guiana, where Ariane Space has their launch facilities. The reason they launch from so far south is that they're nearer the equator. And as the Earth spins around, you know, it goes a little faster near the equator than it does up here where we live, and faster than it does near the poles, and so on. So it's orbiting, it's spinning at about 1,000 miles an hour at the equator, only about 700 miles an hour up here, and less. And if you launch from the North Pole, you essentially get no boost from the spin. So by launching in French Guiana, Ariane Space is able to launch bigger payloads at a higher speed with less fuel, because they take advantage of the fact that the rocket is already going almost 1,000 miles an hour with respect to space before it even leaves the launch pad. So it's worth the cost and difficulty of operating in a jungle environment for that reason. Here's the launch. If anybody speaks French, you can translate for us.
Decolonize liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the cloud.
Now the next video I'm going to show you is the actual release of the Space Telescope from its carrier rocket, giving it the appropriate push to have it travel out 1,000,000 miles and stop at exactly the right spot in space. The spot that they're aiming for is a little gravitational, like golf hole about 1,000,000 miles away called a Lagrange point. Normally, when you go farther away from the sun, your orbital speed has to be slower in order not to go off into space. But there are certain points, and one of them is 1,000,000 miles away from Earth, that the gravitational pull, combined pull of Earth and the sun allows an object at that spot to orbit the sun at the same speed that we do here 1,000,000 miles closer. And so that spaceship, that object, whatever it is, will follow us around the Earth essentially, and won't slow down and fall behind. If you think about the planet Mars, right, Mars is 20 to 40 million miles farther from the sun than we are. We make it around the sun in 1 year. Mars takes almost 2 years to do the same thing. So you can see the farther out you are from the sun, the slower your orbital speed is, unless you're at one of these Lagrange points. They hit this Lagrange point so accurately, they launched the spaceship with exactly the right amount of energy, because as the spacecraft coasts out to this Lagrange point, the sun's gravity is always slowing it down, exactly like throwing a baseball up into the air. It slows down until it reaches a point where it stops, and then it begins to fall back. So if they don't hit that golf, it's like a 1,000,000-mile putt uphill, but it's not a golf hole where, you know, the ball would fall in. It's more like a 1/4-inch divot in the grass. And you have to roll into that and not roll out the other side, and then you can stay there for free. But if you miss it and go past it, you end up coming back and your ball rolls all the way back down to the launch pad. They launched with such precision that they had fuel on board for the thrusters so that they could slow down or speed up appropriately as they approached this spot. They needed almost no fuel to be able to do that. This 1,000,000-mile putt was so accurate that the original guesstimate of 10 years of operation of the telescope based upon fuel consumption on orbit has been extended to almost 25 years. The accurate launch gave us about 15 years of extra science for the same amount of money. So the Area and Space engineers did a great job. So here's that actual launch. This is the final push of the spacecraft, the still folded up James Webb Space Telescope on its way out to the Lagrange point 1 million miles away. That's the last time anybody on Earth will ever see it close up. You can see some extra solar panels stuck on the bottom in addition to the ones that are going to unfold as well. So that was the absolute perfect stroke of the putter. Couldn't have been better. Now, what do we do when we get there? We have to unfold this enormous telescope. So here's what that animation looks like. We've got 5 layers of sun shield to keep the heat of the sun from affecting the instruments. And those are about the size of a tennis court, each one of them. And they have to be unfolded, stretched out in space while we're coasting on our way out to the Lagrange point. So here's a little animation of exactly how that's going to happen. You can see that this mylar material, which is only 1/1000th of an inch thick, has to be pulled out, and then each layer has to be separated from the layers behind it so that any heat that leaks through layer 1 and trying to get to the telescope will actually end up bouncing out sideways and escape sideways and never make it through to layer 2. The same thing happens between layers 2 and 3, 3 and 4, 4 and 5. By the time you get above layer 5 here, and the sun is down here trying to shine heat onto the telescope instruments and the cameras up here, there's essentially no heat from the sun making it through here at all. And that allows the camera equipment to chill down to the almost absolute zero temperature of space and work appropriately. So the secondary mirror has to be extended like this, and then eventually we are now operating. So the sun will always be in this direction. The telescope itself can spin around and look at the sky in any direction, but it can never rotate to allow any part up here to be exposed to the rays of the sun. So it's got 2 sides, obviously. The observing side is where the telescope, the cameras, and the observing struts are. And this is the part that's always in the shade. But the other side that faces the sun contains the solar panel, the radio receiver dish for transmitting and receiving pictures to Earth. You can see the sunshade here, the first layer of the sunshade that's protecting the instruments up here from the heat of the sun. And this little guy here, believe it or not, is actually like the rudder on a sailboat. It turns out that the pressure of light from the sun will actually tip the telescope over and turn it upside down over the course of months. And so they actually have a little rudder here on the back, and they can change the angle of that rudder to balance out the pressure of light on this part, which you see is much bigger. And they can change the angle of that so that it exactly balances the pressure of light that's trying to turn the telescope over. And I forget what they call it, but it's kind of like a rudder on a sailboat, or maybe the skeg that you put down into the water. Quite amazing. So the cool side and the hot side. And here's what it looks like in orbit around this Lagrange point. This Lagrange point, as I said, is an imaginary point about 930,000 miles exactly on the opposite side of the sun from us. And the James Webb Telescope is orbiting this spot in space, this imaginary spot in space, with the warm side on the other side facing the sun, and on this side you can just see the mirror and the cameras and all that, constantly in the shade of this 5-layer level of protection to keep them cool. I mentioned that the Webb telescope is sensitive to infrared light. And infrared light, as I said, is the portion of the electromagnetic spectrum that's just longer wavelength than what we can see in red light. This little part here is the only part our eyes are sensitive to. We call that visible light. And it goes from blue light, you probably remember Roy G. Biv from high school, right? So red, orange, yellow, green, blue, indigo, violet. It's all packed into this one little range of wavelengths. And you might wonder why. What's so special about that? Well, it turns out that the atmosphere on Earth is not transparent to electromagnetic radiation very well in a lot of other places. But for this little range of wavelengths, our atmosphere is quite transparent. That's why you can actually see the 4 peaks when you look at it. And so our eyes have developed, of course, makes sense, to take advantage of the radiation that actually bounces off things and ends up coming into our eyes. So we're sensitive to a range of radiation that exactly matches a little window of transparency in Earth's atmosphere. No surprise there. Infrared light does make it through. Obviously, when you get out into the sun, it feels warm. You can feel all that. But the instruments on the James Webb are sensitive to, there's 3 instruments that are sensitive to what we call the near infrared, which is just beyond red, and then there's the MIRI instrument, which is sensitive to the mid-infrared range, that's kind of over here. A little bit longer wavelengths, but infrared light has the advantage that it passes through intergalactic and interstellar dust very readily. It allows us to see inside clouds of dust and gas that are in distant galaxies, and it also allows the light from those distant galaxies to pass through interstellar dust that otherwise at some point absorbs all the light that's heading to us from distant galaxies, and we can no longer see it at all with regular visible light telescopes. So this was designed to be an infrared telescope because infrared light allows us to see deeper, farther out into space, and to see things that otherwise would be completely invisible because their light would be absorbed on the way to Earth to our telescopes. This is the mid-infrared range, mid-infrared instrument. It contains cameras and a spectrograph. Spectrographs break the light up into different colors and measure how much light there is at different colors. And there's a little animation coming up just to show you how complex this instrument is. Packed into this instrument, you'll see how many different ways the light can be bounced around between gratings, mirrors, reflective components, and then eventually sensors of different kinds. So this is where light from the telescope actually first enters the MIRI instrument. Are you following this? So we've split the light into multiple colors, we're analyzing the different wavelengths, and we're splitting each wavelength up into multiple subgroups, and then we're taking photographs at the same time depending on where the mirrors are positioned. One of the mirrors that has a rotating motor that rotates it around to reflect the light into different parts of the instrument had a little problem. It was binding a little bit. And so MIRI was taken offline for a course of about 2 months while they debugged the problem, and it turned out they just had to push a little harder. They turned up the voltage on the motor and solved the problem, wound it back and forth a few times and cleared the friction. And so obviously instruments like this have to be lubricated with grease that won't evaporate in a vacuum and then go and coat your mirrors with junk so you can't see anything. So the whole design for things that operate in zero gravity and vacuums of space is a real engineering challenge as well. So here is the first picture of a star taken by the James Webb Space Telescope. What the heck is going on? That's one star, but if you count them, there are 18 dots of light here. Well, 18 is the number of mirror segments that we have in the telescope. They haven't been aligned yet. On the back of each mirror segment are little motors and electromechanical devices that can nudge those mirrors into perfect alignment with each other, and that hasn't been done yet. But what they had to do was figure out which one of these dots came from which one of those mirror segments. That was something that they knew they'd have to do. They were ready to do it, and it turns out it was fairly easy to do. So this set here came from the left wing, those 3 mirror segments that were unfolded. This group of 3 dots came from the right wing, the right side 3 mirror segments, and all the other dots came from the various other segments. So now it was a question of just sending the commands up to the telescope to say, okay, this one has to move this way, that one has to move that way, and after all that was done, and it only took a few days, now we've got the still out of focus, but properly aligned mirror segments. And now every one of these dots is in exactly the place that corresponds to the position of the mirror segment on the truss out in space a million miles away. And the last step was simply to focus them. And so when we finally complete the alignment and have them in focus, we know that each mirror segment is in focus, and now we move the mirror segments so that they actually move all these dots into one place, and in the end we end up with an image of a single star that has absolutely no aberrations to it. We don't have the Hubble problem. The reason that you see the six lines here is because optically there's a situation where any edge of a mirror provides a certain amount of interference to the image. And in this case, these are hexagons, and so you'll always see 6 of the 3 crossing lines giving you 6 edges. Each one of those little lines represents the interference caused by the edge of one of the mirrors, and you can see they're all almost perfectly aligned. In my telescope, and I know in Scott's telescope, we have a secondary mirror that's carried by a little set of wires that make a cross. And we always see 4 lines around our stars because we have 4 little lines interfering with the light. But in this case, there are 6. And here's what the first color image looked like. Again, in light that's invisible to the eye, but each one of these wavelengths that's received can be assigned to a different color that we can see. So every time the telescope takes a picture in multiple wavelengths, we can pick any 3 visible colors and say, okay, this part of the infrared spectrum we're going to call red, this part we're going to call blue, this part we're going to call green, and out comes a picture that actually makes scientific sense and conveys information to our eyes that we can then stare at and study. And we can change which colors we assign that to. We can change the intensity of each color depending on which part of the infrared radiation spectrum is most important to what we're actually studying. And so that's how pictures that are in invisible light become pictures that we can actually see. Over time, the resolution of these infrared telescopes has gotten way better. This is the WISE telescope, which studied infrared light at 4.6 micrometers, which is a very near infrared light. Here is what the Spitzer Space Telescope looked like. This is exactly the same area of space with these same stars, but you can see that as technology improved, we can improve the resolution, and now we can see these stars more accurately. We can see a few stars here that weren't even visible in the original image. I mean, this is state-of-the-art back in the 80s. This is state-of-the-art in the 90s. And then this is what the James Webb Telescope is able to provide for us in the same area of the sky. I mean, just gazing at that, you can see the incredible difference that a huge mirror, super cooled cameras, and a really, really perfect engineering set of tests was able to deliver for humanity. So what's the benefit of all of this work? The real goal of the James Webb Telescope is to study the time period during which galaxies were first forming after the Big Bang. That time period since the Big Bang is about 14.5 billion years. Our solar system formed about 4.5 billion years ago. So our sun is about a third as old as the entire universe if you consider the beginning to be the Big Bang, roughly a third. As we look out into space, every telescope is a time machine. Everything you look at is a certain distance away, and the farther away it is, the longer it took its light to reach us. And so you're seeing it as it was long ago. We have a bright place in the sky called the Orion Nebula, where stars are being born. And if you had a friend with a telephone on a planet around one of those new stars and they gave you a call, it would take about 1,500 years for your phone to ring. And when you said hello, it would take about 1,500 years for them to hear your voice. So slow conversation. I tell the kids at our telescopes, that's the only friend you can talk to on the phone while you're doing your homework. Because it's definitely not going to interfere. But that's like the closest place in our galaxy where things are actually happening like that, where stars are being born. Our galaxy is about 100,000 light years across, so that phone call from one side of the galaxy to the other would take 100,000 years for the phone to ring on the other side. 100,000 years, though, remember, the galaxy, the universe, happened 14.5 billion years ago. So that's 14.5 million thousands of years. The universe is an incredibly more vast place than our little local galaxy can even begin to imagine. So as we look out in space, we see distant galaxies. They take us on a time trip back in time. And the Hubble Space Telescope, you could see back to about here, about 1.5 billion years after the Big Bang. So there were interesting things happening there, but many of the galaxies in the universe had already formed. Not ours, we're kind of a latecomer, but the early galaxies had already formed. So we could tell that something interesting had happened, but we couldn't quite see it happen because the light from more distant areas of the universe had to travel through more and more dust, more and more interference, and was absorbed by this material. So we were kind of stuck right about here at about 1.5 billion years after the Big Bang. But the James Webb Telescope, because it's sensitive to the infrared light that can pass through clouds of dust without absorption, can see back almost another billion years or so. So this is where the first galaxies were forming. The James Webb can see almost as back to where the first stars in those galaxies were forming. So we really get a trip back through a very interesting part of the universe's formation that we couldn't really see with visible light telescopes like the Hubble telescope. So the James Webb, because it shifts into the infrared, allows us to take a look back almost another billion years towards the beginning of the universe, almost to the point where what we call the Dark Age, which is before stars even formed. So before there were any light coming out at all. Big Bang Theory is another, whole issue. I'll leave it at that, and just to give you an idea that this gives us a way to see almost back to the point where beyond this, there aren't any interesting things happening that we can see because no light is escaping. So there's nothing to tell us what was going on. Light brings us news of the universe. Okay, that was said by somebody in the 1920s. And with no light, there's no news. So we learn everything we can from light, whether it's visible light, infrared light, X-ray light, gamma ray light. It's all light from the electromagnetic spectrum, and that tells us the news of the universe. So James Webb can tell us that. If we look back in time, this is a deep field image taken by the James Webb Telescope. Now, the Hubble took a deep field image like this that some of you may have seen, and they exposed the camera for 10 days, every orbit for 10 days. The Hubble goes around the Earth every 90 minutes, so 45 minutes of every 90 minutes is in the dark, and they can expose. So for 10 days, they stared at the same spot in the sky and determined that there, in this one tiny little point where you couldn't see any stars, there were over 1,000 galaxies visible out in that direction. The James Webb Telescope took this picture in 12 hours. And it has more images, more galaxies visible in it than the 10-day exposure from the Hubble telescope back about 25 years ago. But one of the things in here is this little red dot, and that turns out to be one of the most distant galaxies ever visualized. This galaxy happened only 1/3 of a billion years after the Big Bang, 350 million years after the Big Bang. It's one of the oldest objects that anybody will ever see, and it was imaged in this deep field image, where every object in here is not a star, but a galaxy like our Milky Way with hundreds of billions of stars in every one of these little galaxies. Some of them are really well formed. Those are kind of the ones that have had time to evolve into a nice spiral formation, and some of them are just blobs that haven't really had time yet. They're farther away, their light is coming from them from earlier in their evolution, and we haven't seen them actually evolve into something more structured in the time that they've had to be alive, to be in existence. So here's another photograph from the James Webb showing how a star, a young hot star, can send out radiation in all directions and actually clear out a huge bubble of space inside of the cloud of dust and gas that actually gave it birth. It's kind of a race. The star, of course, because of its gravity, is sucking in new material all the time from this cloud, but at the same time, it's pushing all this material away as it gets bigger and hotter. So it's kind of a limiting, there's a limiting race going on between how big can a star actually get before it actually blows away all the material that would make it bigger and sends it off into space where it might encounter another young star and get absorbed into that star. So it's a process of multiple stars all being born in the same cloud, and you can see lots and lots of these bubbles where these stars have evaporated some of that material. Here's a little difference of the Hubble versus in the Hubble telescope. The Hubble telescope instruments are actually sensitive to slight amount of infrared light. They can see slightly into the infrared. They're not totally visible light limited. So this is what the Hubble can see in visible light, and this is what it can see in infrared light. You can see how in infrared light we can see through a lot of this haze, a lot of this material, and see much more higher resolution image of those stars and basically forming young hot stars being born in this cloud of dust and gas. More resolution means scientists can learn more about what's actually going on and figure out which stars are younger, which ones are older. They can look at the spectrum of each star, learn about the gases that make it up. The light tells us all the news we need to know, but if it gets absorbed by the clouds of dust, we lose. So seeing in infrared gives us a real benefit. This is a picture of the Carina Nebula, something that's only visible from the southern hemisphere. But this has been a beautiful image that the Hubble has provided, and people have been gazing at this in awe for decades. You can see here's up here out of off the screen is the young hot star that's actually carving out this bubble in the original cloud of dust and gas that gave birth to it. Keep an eye on that little bump there. We're going to show you what the James Webb was able to show you. Same image. There's that little bump, but you can see the difference in resolution. We can see deep, deep into this cloud of dust now. We can see hundreds of more stars being born. We can actually see through this dust to the stars that are way out in the background. I'll go backwards and forwards here just for a second. This is the best the Hubble could give us, and it was fantastic for its time. This is what the James Webb was able to do within the first month of its... in fact, this was one of the first 5 photos returned. You might remember there was a big press release with the first 5 photographs, and this was one of the first 5 photographs that they released to show just what the James Webb telescope could do, because they had a Hubble equivalent image, so we could immediately see that our money was well spent. This is another one of the James Webb deep field images that was taken with maybe 12 hours of exposure. And interestingly, they noticed that there were these curved objects in here, and those turned out to be images of galaxies that were far in the background behind this cluster of galaxies. And the gravitational pull of these galaxies was doing something that Einstein predicted might happen. That they would serve as a kind of a lens, and they would take that light that's coming from the distant galaxies and bend it around them because of the gravitational pull, and it would come to a focal point out in front, so you could actually see around the corner because the galaxy was bending the light that was coming out and otherwise would have gone out into space. And that is exactly what happened. These are called Einstein rings. And this is a diagram of that galaxy's gravitational pull. And here's the light coming from distant galaxies. It's getting bent around this galaxy cluster with its huge gravitational pull, and it ends up being able to be focused by the James Webb telescope into an image that is stretched out into this ring. But by analyzing the light in the ring, we can tell what kinds of galaxies those are, the ones that are way in the distance. Otherwise, it would be invisible. So Einstein predicted that space would curve and that light would curve in the presence of a large gravitational field. And we know that Arthur Eddington demonstrated that to be the case during an eclipse back in the 1920s. But here's another example that Einstein was right again and again and again. Here's the Southern Ring Nebula, another example of a star's in its death throes, essentially. This star has sort of burped off its outer layers during the process of getting older, and some of those outer layers are moving out into space at high speeds, 40,000, 50,000 miles an hour. But when you look at that with the James Webb Telescope, you see a huge amount of detail in this cloud that tells you a lot more about the process that actually formed that actually ejected this material out into space. You can actually tell that some of this material was ejected at a higher speed than others. It went out in layers, and it didn't all happen in one giant poof. It apparently happened multiple times because there are concentric rings of material that are farther and farther apart from each other. This is a set of galaxies called Stephan's Quintet that we can actually see here. I think it's in the constellation Virgo. Maybe Scott can help me.
Not sure.
Okay, he says maybe. Definitely Virgo. And you can see this beautiful set of galaxies. They're actually interacting with each other. The gravitational tug of these is pulling millions and millions of stars out into this stream of stars that we don't know whether they're ever going to curve back or not, but essentially galactic collision going on here. And this is a picture of a galaxy in black and white called the Cartwheel Galaxy, taken by the near-infrared camera. But when we shift that into the visible light from the infrared, you can see the detail that we get. We can learn about the blue areas where young stars are forming and red areas where older stars are living out the last parts of their life. So we've got incredible detail coming from having high resolution and multiple different wavelength bands to be able to see. The James Webb can also look at planets, and it took a look at Jupiter, and we saw Jupiter in a way that we've never seen it before, because we can see farther into Jupiter's atmosphere than we can see in visible light using infrared. So here's an infrared picture of the planet Jupiter that some of you have, of course, you've seen it in telescopes. You know that it has cloud bands, horizontal cloud bands. Jupiter is 10 times the diameter of Earth. Okay, so Earth is about the size of the Great Red Spot. 1,000 Earths would fit inside Jupiter, and Jupiter rotates in just 10 hours on its axis. 10 times the diameter of Earth, and it only takes 10 hours for a day to go by. So it's really spinning around quickly, and that's what drives all of this convection and turbulence in its atmosphere. But in the infrared, we can not only see that, but we can actually see the faint ring that was discovered by the Voyager spacecraft in the 70s when it went by. This is this Jupiter's ring is very faint, invisible from Earth, completely invisible, but visible from the James Webb 400 million miles away, but only because of infrared light being reflected off these rings. And these are a few of its moons, in a couple of moons here and a moon here as well. And this, we determined that Jupiter has auroras, the northern lights and southern lights, just like we do on Earth, based upon magnetic electronic particles from the sun hitting Jupiter's atmosphere and being deflected in from Jupiter's magnetic field. The James Webb has also detected gases on other exoplanets. That an exoplanet is a planet around a star other than our star. And we can not only identify that exoplanets exist, but we can analyze the light coming from those exoplanets' atmosphere, reflected or passed through from their parent star, and determine what kind of gases are present in the atmosphere of a planet around another star. And in this case, we see a peak in the spectrum in the wavelength of light that corresponds to what we see here on Earth from the gas carbon dioxide. So we're able to say with certainty that there's carbon dioxide in the atmosphere of this particular exoplanet. Doesn't mean there's life there, but very interesting. If we find a gas like methane, methane is a gas that that we know is quickly degraded by ultraviolet light and is only produced by living creatures. So looking for methane is one of the ways we're looking for signatures of life on exoplanets in other solar systems. This is a classic picture called The Pillars of Creation. This was my screensaver for years when it first came out. I love looking at this. Again, this is a situation where you've got clouds of dust and gas and a huge, bright, hot star up here off the screen that's carving away this pillar of dust and gas because of the intense radiation pressure that's coming from above. And we just happen to catch it in this beautiful, beautiful way. But take a look at that same image from the James Webb Space Telescope. And you can see the difference in resolution and detail that we can get from being able to see farther into the infrared. And of course, the bigger your telescope, the better the resolution you can get in any picture or image or visual image. We call that aperture fever in the amateur telescope world. And it tends to deplete the household finances over time, unless you're really careful and get inoculated against it. And there's no inoculation, there's no vaccine against aperture fever once you've seen the telescope. A bigger one's always better. This is the Halloween image that I love. It's a creepy looking thing that you might imagine is out there in space, and that was imaged again by the James Webb. And this is the rings around Neptune. Again, discovered by Voyager back in the 70s when it zoomed past. We haven't seen them since, but the James Webb is able to image Neptune's rings very easily. You can see some of its moons and so on. You can even see some of the reflective atmospheric clouds in the atmosphere of Neptune. So we can do close-in work in the solar system as well as distant work out there. This is an image of a spiral. It turns out to be face-on to Earth, so we can see all the detail as the stars evolve, as they spin around what's likely a giant black hole, just like we have in our galaxy that keeps all the stars organized and spinning around. But again, high-resolution image, beautiful, and lots of scientific detail here. This is a picture of that star-forming region that I mentioned in the Orion Nebula. And you might notice the name down here, Scott Adams. Scott is sitting right over there. Raise your hand, Scott. Scott is our premier Fountain Hills astrophotographer, and this is one of his beautiful pictures of this incredible area in the Orion constellation where stars are being born. And
with an 8-inch diameter telescope.
That's right. That's right.
From my backyard here in town.
From his backyard here in town. So kudos to Scott. This is quite an achievement, and he's been working on that for maybe a year and a half. So he's a quick learner, I got to tell you. That's because astrophotography is like a different hobby compared to looking through a telescope. It requires a whole different set of skills. But here's one of the James Webb images, close up of that area, right in here, where a lot seems to be going on. And so you can actually see young stars being born inside this cloud of dust and gas, just like our sun was born in a similar cloud 4.5 billion years ago, and our planets were formed out of whatever was left over after the sun gobbled up everything it could. This is another young star that's blasting out streams of gas in both directions as it consumes a lot of material, but also ejects it out of its north and south poles, which are just sideways. And again, like a couple of other images like this, analyzing the light from stars. And this is the first identification of an exoplanet by the James Webb Space Telescope. So around this star, we were able to zoom in on it. There's the star, blocked out by a little filter inside the telescope, but here is the exoplanet in 4 different wavelengths of the different instruments, and this is an actual detection of a planet around that star. As bright as it is, the James Webb was able to zoom in and take images of that to identify that it actually has planets around it. And here's a zoomed in image of one of those as well. You might remember a couple of months ago the DART project was successful in driving a space craft that weighed about 14,000 pounds into the moonlet of an asteroid to see if we could deflect that little moonlet and possibly get some data on how we could someday perhaps push an Earth killer, a dinosaur killer type of asteroid off its course and save the planet. And this was very, very successful. And what you see here is a picture a few seconds after the impact, both in the Hubble and in the James Webb, of the blast of material that was ejected from this little moonlet after the DART spacecraft smashed into it. You can see on the Webb the actual photographs that it took as it got closer and closer and closer. Dead center strike right on this little 500-foot diameter moonlet after a 6-month journey out into the asteroid belt. So studying this, we learned a lot about the kind of impact we had on that, and we actually changed its orbit by about 5 times more than anybody thought we would. So the data supports the idea that someday, if we needed to, we could deflect an asteroid that might be heading for Earth that would end all life on Earth and maybe save the planet. So it's nice to know we could do it, and if we need it, the data's on the shelf. We can figure out how to do it again if we need it. Yeah. I want to show you this one. This picture, we're close to the end here. This is that same picture I showed you earlier, turned sideways. You've got a bright young star in the middle forming inside of a cloud of dust and gas, and it's ejecting material out its north and south poles right in there. And this little bar that you see here, that's the disk of dust and gas that's giving birth to this star and some planets around it. That light, that is so thick, that's so thick that it's actually blocking the light from the star that's coming out towards us. It's as if this is a Spitzer Space Telescope picture of a different star forming what they call a proto-nebula of a solar system, a proto-solar system, and you can see it's kind of like that. So there it is, right there. That in there is a star beginning to absorbing all the material it can, and whatever's left over after the star has absorbed all it can may end up into planets, just the way we did here in our solar system. So let me recap real quickly here. The James Webb Telescope, it orbits this million-mile point outside of our orbit called a Lagrange point. There are 5 of them in the solar system. They were identified by a French mathematician, Lagrange, back in the 1800s. We could put something in any of them, but this one's closest, and so it makes sense to use that one. It's sensitive to near and mid-infrared wavelengths of light, not to visible light, but to near and mid-infrared wavelengths of light. And the instruments have to be very, very cold in order to be able to sensitive to that. So that's why it's all that reflective material, keeping them very cold. The advantage of this, as I mentioned, is infrared light passes through dust without being absorbed as much as visible light does, so we can see farther and deeper into space. Deeper into space means farther back in time. Farther back in time means we get to see more interesting details about formation of the stars, formation of the galaxies, what happened immediately after the Big Bang, and things like that. And the most distant galaxy that it has seen was created when the universe was only 2% as old as it is today. That's a huge step back in time. So hopefully we'll expect many more discoveries for the next 25 years. So I thank you. You've been a great audience. I appreciate your attention.